My name is Geoffrey Darnton. I'm the chair of the RSS Reading branch, and this is a Reading branch meeting. And it should be, well, I'm really looking forward to it. So the presentation will actually be given by James Taylor. He is Professor of Decision Science at the Saïd Business School at Oxford. I'm sure most people will have heard of the Saïd Business School and of Oxford. Surprised if people haven't. He's a former associate editor of the International Journal of Forecasting and Management Science. So it's an interesting combination, forecasting and management science. But of course, like much decision making, it's supposed to be evidence-based. But quite often there's that conflict between political decision making and evidence-based decision making. So he did his first degree in maths at Cambridge, then second degree operational research from the University of Lancaster. I spent some time at Lancaster myself. The PhD in time series forecasting from the London Business School. I don't know whether that was the times of Michael Earl or not, but I used to be dealing with London Business School in Michael Earl's days. And now he's currently at Saïd Business School. So you all have the title for the talk. It's on the screen at the moment. So as was mentioned by Nachi at the beginning, if you have questions, I think, James, you're quite happy if people interrupt if they wish to interrupt. So you can raise your hand, your virtual hand, best using the technology, or wait until questions and answers at the end, or use the chat box. So there are 3 different ways to be able to ask questions if you'd like to ask questions. So can I hand it over to James? Would you like to present?
Yep. Thanks, Geoffrey. Thanks for the introduction. Thanks for the invitation. Very honoured to be giving the talk. Thanks everybody for coming along. I mean, Geoffrey's sort of outlined several different ways of sort of raising a query. I might not notice, but one of the other guys will do, and they'll interrupt and give me a shout. Right, so I shall proceed. And supposedly you can sort of see and hear. I can at least see Geoffrey, so he can pull a face if he can't suddenly hear me or see me. Right, well, there's the title, Harnessing the Wisdom of a Crowd of Probabilistic Forecasters. Contents. I want to give a little bit of background, and then I'll charge on into the data that I've been analysing. And it is US COVID mortality data. Some data sets are evolving in this country, in Europe, but actually they're not as rich as the one that I got hold of that relates to US mortality. So that's the data I've been using. And I want to talk a lot about interval forecasting and distributional forecasting. I wonder whether I will have time to talk about the last bullet point, which is data from the Survey of Professional Economic Forecasters. If I don't, well, actually, the methods I'll have talked about before are the methods that I'm using for that sort of data, so that wouldn't be too big a problem. Let me charge on into the background. I think I probably should define roughly what I mean by probabilistic forecasting. Okay, well, there's a time series. Doesn't matter too much what it is. Seems to be of the order of thousands. If you can see me sort of looking across to my left, it's because I've got 2 monitors here. So I'm looking at the presentation on the left here. And the time series sort of seems to fluctuate up and down. You can see that it stretches back to the start of last year, near the start of last year, and it's weekly data. And what you can see out the end, the right end, if I can point at it with my highlighter here, is a set of forecasts. So I've got forecasts here for whatever this is, this product, whatever it is, for the next 4 weeks. And that would be, I suppose, the line there through the middle, that sort of fairly horizontal looking projection would be point forecasts, central point forecasts, best guess point forecasts. But wrapped around, projected out into the future, there's also, it seems, interval forecasts. These are 95% intervals, and these are a form of probabilistic forecasts. By probabilistic forecasts, I suppose I mean measures of uncertainty, some way of conveying the uncertainty in a forecast. And an interval is a pretty sound way, a pretty common way of doing that. Another way of doing it would be to present the full distribution. So very patronizing to present this slide to an audience like this, but maybe this is just for notation or just to make it clear when I refer to a distribution, I'm probably thinking of the CDF, the thing on the right. I won't talk very much at all about densities, the density form of a probability distribution, the thing on the left. Oh, but I might refer to quantiles a bit, and I suppose a 95% interval would be bounded by the 2.5% and the 97.5% quantiles. I hope that's all right. What else to say? Oh yes, on the right, for the distribution, the cumulative distribution function, the distribution as I'll casually refer to it, yes, I've got the quantiles there, the 95% interval. I'll show you that sort of picture for real data later on. So I just wanted to make sure we were all on sort of the same page, as it were. What else to say about quantiles, intervals, and distributions? Well, if you're going to produce a forecast, an interval forecast, you probably want, like any sort of forecast, to be able to evaluate its accuracy. I suppose if we're talking about producing intervals for some future period, intervals period by period, then I suppose a fundamental way of evaluating the quality of it is whether, I suppose if it's a 95% interval, whether in the long run, 95% of the observations fall inside my intervals. Yes, that would be calibration. That would be coverage. But actually a measure that captures coverage and more is a score. So this is quite possibly my most technical slide. So apologies to the mathematicians out there, but you see, we use a score all the time in forecasting. We use a score to evaluate a best guess point forecast of the center of the distribution, of the mean, if you like, my best guess point forecast. Anybody who's done any forecasting probably has used mean squared error. Yes, use the squared error to evaluate a forecast of the mean. Absolute error, actually, to evaluate the forecast of the median. And for a quantile, let's have an error measure for a quantile. Well, here it is, okay? In the middle of the slide there, I've got an expression, that's the tick loss function, some people would call it, tick loss. Seems to actually indicate, it seems to sort of summarize the deviation of an observation from the quantile forecast. Oh, it's a weighted deviation, all right? There's the indicator function there. Indicator function being 1 if the element inside the parentheses is true. So it seems that you've got a deviation weighted by alpha if you've got your observation greater than the quantile forecast, and alpha minus 1 if the observation is less than the quantile. I want to leave it there. That I'm going to refer to as a quantile score, and that will be a summary of how accurate my quantile forecast is. All right, what about an interval forecast? What if I'm producing an interval forecast? What about the accuracy of that? Well, I suppose you could take the quantile at the upper end of the interval and the quantile at the bottom end of the interval, and you could sum the two corresponding two quantile scores. And that's used a lot to evaluate an interval forecast. Okay. Oh, what about a distributional forecast? What if you were forecasting the whole distribution? All right, well, I'm interested in all of the alphas then, aren't I? And if you take that expression in the middle of the slide and you integrate over alpha between 0 and 1, then you've got yourself a score for the full distribution. And that's known as the continuous rank probability score. That's the CRPS. That's at least one way of looking at the CRPS. And that's a score, an error measure for a distributional forecast. Okay, so I don't really, the details of this slide, I really am not going to be using again, but I'm interested in just that idea that there exists a summary measure for the accuracy of interval forecasts and for distributional forecasts. Right, more background. Okay, well, if anybody's talking about wisdom of the crowd in the context of forecasting, they're probably talking about combining forecasts. And actually, wisdom of the crowd has become quite topical. It seems, I suppose, that it's a modern sort of topic. Well, combining forecasts is not a modern topic. It's as old as the hills. Formally, it stretches back to about 1969. Bates and Granger, the first formal paper on forecast combining. That's the great Clive Granger. Forecast combining. You can sort of see at the bottom of this slide an expression, a combination of forecasts. My Y hats are my individual forecasts. So this is not a crowd. I've just got 3. Now, why would you possibly combine forecasts? Why wouldn't you just take the best method, the best model? And I'm trying to answer that in the first bullet point. Often the best is not very clear. Maybe one method is often the best, but it's not always the best. Maybe others have value. So what an economist, an econometrician might say is build a better model. And that's a fair thing to suggest. However, maybe it's not so easy because maybe your forecasts are coming from very different, very different sort of methods. Maybe one is coming from a regression model and another is judgmental, coming from some expert. How are you going to sort of bring that information together into a new, better regression model? Well, it's not easy to do. So what people typically do is they combine. And what combining is, it's basically a pragmatic synthesis of the forecast information. Another way of looking at it is that a combination like that expression at the bottom of the slide is a portfolio of forecasts. Why are we forming a portfolio? Why does anybody ever form a portfolio? I suppose we're diversifying the risk. We're diversifying the risk of, I suppose, selecting a method that turns out to be bad. Yeah, so that expression at the bottom, I suppose, could be viewed as a portfolio of forecasts. I suppose if it's a portfolio, probably the weights, the W's, would sum to 1, and W subscript 0, the intercept term, if you like, that would be 0. Yeah, you could have that form of combination. There's lots of different forms of combinations. I'm sure there's 1 or 2 Bayesians out there, and there's Bayesian methods for combining forecasts for sure. But what's quite irritating and a bit frustrating, and I think it's referred to as something like the combination puzzle. The puzzle is, why does the simple average work so well so often? So that's a sound benchmark for any study of combining forecasts, the simple average. Very frustrating, but we must remember that if I start to combine later on. Right, okay, enough on that background. Well, it's all background, really. There's not very much that's very new in this presentation. The work I've done in this area has largely been applying other people's ideas. Okay, well, I don't come from a very classical education, so I'll have to just believe what I've been told. Vox, is it Vox Populi? Populi, Voice of the People. Okay, was the title of a paper by Francis Galton, a celebrated statistician, polymath indeed, an expert in many things. And he'd retired to the southwest of England, God's own country down there. I was brought up in Plymouth, and it was in Plymouth that he attended a country fair in 1906. And he was quite interested in, well, he was quite interested in measuring things, and slightly controversially, he was quite interested in eugenics. He was quite interested in breeding. And I suppose he took the view that actually your average person shouldn't be trusted with a vote. The average person doesn't have much wisdom. Okay, well, anyway, he was at this country fair and he noticed that there was a competition going on to guess the weight of an ox. 787 individuals submitted guesses, And he took note of the median, and later on, harder in those days, but he did calculate the mean. And what he was staggered to find was actually the true weight of the ox turned out to be 1,197 pounds, spot on, the mean. So it turns out that the average of this population was extremely full of wisdom, it could be said. Okay. The picture down the bottom is, well, I don't really want to look at that, but that's just a distribution, a histogram of the different guesses. So you can see there's quite a lot of variability in the guesses, but on average, they got it right. So that was one in the eye for Francis Galton. This is quite a good book. This is quite easy reading, very popular, big selling book. I won't try and, or perhaps I will try and pronounce the author's name, James Sariecki or Viecki. Anyway, it's good read, and it really brought to prominence and I suppose widespread attention the concept of wisdom of crowds. And he highlights a number of conditions which you need to have an informative crowd. Motivation. Yeah, I think they had that at that country fair in Plymouth at the start of the last century. They were motivated. There were prizes on offer. Diversity. I think you certainly had diversity there because you had sort of what could be considered experts. You had farmers, probably used to sort of dealing in the weight of oxes, and you had sort of ordinary folk. So you had a lot of diversity in the guesses coming in. Independence? Yeah, I guess so. I mean, probably there wasn't a lot of cheating, collusion, sneakily looking at other people's guesses. People just submitted their own and didn't show others. They wanted to win the prize. There was independence. Decentralization. What that's sort of referring to is there was nobody from above telling people, directing them in their guesses. People just used their own local information. Information, the key sort of term in this crowd business, this combining business. And there was a trustworthy mechanism for aggregating opinions. I suppose so, yes. Okay, so what about other applications of wisdom of the crowd? I won't go through all of these, otherwise I simply won't get through anywhere near the right number of my slides. One or two of these have been pinched shamefully from Wikipedia. Who wants to be a millionaire? What works quite well is to phone a friend. Apparently about 60% of the time, they get it right. But what works well more than 90% of the time, apparently, is to ask the audience. Wisdom of the crowd. What's that fish doing in the middle of the slide? That's the golden shiner. The golden shiner likes shade, but is not that great at finding shade. The golden shiner finds shade much more quickly if the fish is in a large shoal. And they've experimented, and a small size shoal is not as good as a larger shoal. So there's the wisdom of the crowd in some sense. And that's a lovely murmuration of starlings down the bottom left. Okay, yeah, financial markets as a crowd, or wisdom of the crowd extracted to obtain the price of the asset or whatever. And I pinched this picture here off the ECMWF, that prestigious weather centre, located near Reading, of course. They produce weather ensemble predictions. And I suppose at the heart of what they're doing is some sort of wisdom of the crowd, in a sense. What they find typically, at least when I played with that data, I found that actually by looking at the average of these ensemble of predictions, rather than produce a single best guess for the atmospheric conditions, the state of the atmosphere tomorrow lunchtime, they're producing not just that one, but 50 others. So they've got an ensemble of predictions of say, temperature tomorrow lunchtime. What they find at the average of those 51 is typically more accurate than sort of running the model at high resolution. And down the bottom right, that's some sort of pathetic attempt on my part at machine learning, some sort of summary of an ensemble of machine learning regression trees in this particular case. Rather than produce one regression tree and base your prediction on that, what is considered to be much more sensible is to produce 500 and take the average prediction. If they're classifiers, build 500 trees for classification and then do majority voting. Yes, the wisdom of the crowd, all kinds of applications. Google search engine as well. All right, okay. I must keep an eye on the time because I'm inclined to go far too slowly. At last, to the data that I've been playing with. Right, this is a printout of the website produced by the website run by Nick Reich and his team at the Reich Lab, based at the University of Massachusetts at Amherst. Now, if you Google COVID-19 Forecast Hub, you will get sent to this splendid website, and it has rather good visualizations of this rather morbid, sad topic of COVID-19 mortality. Also has visualizations for case numbers as well in the US. The hub, what's it about? Well, it's about visualizations, which are apparently useful. Useful for what? Well, I suppose for sort of policy making, just to inform the country of how cases are going, mortality is going. But let me focus on mortality. What else is the hub for? Oh, the hub is a means by which forecasters can submit week by week. Yes, they're looking at weekly data, week by week, their forecast for mortality for the next 4 weeks. All right, so it's a hub in that sense for submitting their forecast. It's also a hub from where you can get these wonderful forecasts and carry out research in this interesting area. All right, let me just sort of look at this visualization, this page here. What have we got? Oh yes, well, if you were to go to the website and click on this button here, you can see mortality over time for, oh yes, well, I'm looking here at the US national picture, and you can see it climbing from very low at the start of last year to very sadly above 500,000 now. This is cumulative deaths. All right, if you click on that US national there, you can actually select mortality for each of the 50 different states plus the District of Columbia, DC. So actually, this is what I analyzed in my sort of analysis, was these 52 different time series, US national, and if you like, 51 states. You could click on cumulative deaths, and instead of looking at cumulative deaths, you could look at week by week total deaths for that week. Right, towards the end, can you see over here, there's projections. It's not very, very clear, is it? But what it's showing on the visualization is forecasts from many different forecasters. They've submitted their forecast. Actually, what they submit is a probability distribution for mortality for each of the next 4 weeks. That might be a little bit more clear on the next slide, which is for, oh look, I've clicked on incident deaths here. So this is incidence, and if I refer to incidence, I'm talking about, in Nick Reich's language, it's sort of the total for that week. So you can see those spikes there. Yeah, they weren't doing terribly well back there in the spring of last year. Things got better, and then the things were very rubbish around the early months of this year, this calendar year. And indeed, they were here in the UK as well, in many countries in the world. But I was talking about forecasts. And if you look at the end, can you sort of see that you've kind of got multiple different projections out into the future? And what I clicked on, somewhere else, you can select 95% intervals. And so from each of those forecasting teams, we're getting a 95% interval forecast, and that's being displayed on the visualization. Now, Nick Reich has gained a certain amount of publicity with this. It's a really good project. It's a good contribution, I would say. And the CDC, the Center for Disease Control and Prevention in the US, which is something like their public health agency, National Public Health Agency in the US, have picked up on it. And they're displaying this collection of forecasts week by week, and actually accessed this earlier this afternoon. So it is as up to date as it could be. This is incident deaths, week by week totals for the US, coming down, thankfully. And these are the forecasts. So this is perhaps a nicer picture of what's going on. And each of those lines out into the future is the forecast from a different team. That would be a central point forecast for each of the next 4 weeks out into the future, along with a 95% interval. So that's conveying the uncertainty. So you can see this is right up my street. Now, what about on the right? Now, this is very much Nick Reich's theme as well. From the outset, he's been interested in combining, trying to extract the wisdom of the crowd. And so he's basically looked at all those forecasts, and initially he was taking the average. Now I think he's taking the median, but he's producing an ensemble. And there's the ensemble point forecast out into the future. And what about that red area? Oh, dark pink. That's a 50% interval going out into the future, and 95% bands there going out into the future. So there's this is, I nearly said the game. I mean, it's such a serious topic. We should sort of trivialize it as a game, but this is the enterprise of the COVID-19 forecast hub. Okay, well, lots of different methods. And how many do we typically have? Apparently over there, that looks to be, I think I counted it earlier, 34 teams have submitted forecasts for the next 4-week period. Let's look at that in just a little bit more detail. Oh, what I forgot to point out on Nick Reich's visualization on the website is he works in terms of epidemic weeks. So from the start of the epidemic, around about Christmas of not last year, but I suppose the year before, 1999, he's counting epidemic weeks. So week 18 is about April. And in my data set, I worked with 40 weeks, taking me up until the end of January. Over that 40-week period, you can see the number of teams contributing to Nick's forecast hub rose up until typically he's getting about between 30 and 40 teams submitting forecasts each week. Now, the title of the slide is diversity, because I think I mentioned it earlier. Conditions in order to get wisdom from a crowd. One of them, I think, was diversity. And I think this is a bit of a brief summary, but I wasn't brave enough to break down the different forecasting teams more carefully, but that would probably be interesting to do. But compartmental models, about half of the teams are using those. SEIR models, all right? So epidemiological models. What about the other half? The other half of the teams are using sort of statistical methods, machine learning, perhaps other sorts of methods, agent-based simulation models, but there's a lot of sort of statistical methods varying in sophistication. All right, I've got another picture here to summarize those teams. I just said to you, I'm looking at between weeks 18 right up to week 57. That's about 40 weeks in my data set. How many teams? Oh, on the y-axis, 49 teams have entered forecasts over this period. But what I'm trying to show with this picture, put together by my dear co-author, is availability of forecasts. Do you see the picture that I'm trying to convey, that we're trying to convey? If you see, let's look at a particular, let's look at forecasting team number 1 down the bottom. The big black dot indicates that forecasts were available for all 52 series, US national plus 51 states, for each week. Oh, sorry, not quite each week. I've got a gray dot there. Oh, for nearly all of those 52 series, for nearly all of the weeks. But can you see that for some of the teams, there are quite a lot of gaps, or are there some white circles? And that's indicating quite a lot of series were missing in terms of the forecast submitted. And what you can see at the top of this chart, I suppose, is forecasting teams that have only just entered. I nearly called it a game again. It's too serious. I shouldn't trivialize it to that. But the competition, it's not really a contribution. Sorry, it's not a competition so much as a sort of collaborative effort. Some of the teams are quite new to the collaborative effort, and we haven't got much of a history on them. This is quite important to acknowledge because it probably affects the methods that can be used to extract the wisdom of the crowd, to combine the forecasts. If you like, I'm standing there at week 57 thinking about how to combine the forecasts they've just submitted. Well, I haven't got a complete history for these guys. So how am I going to do a weighted combination? In the language of perhaps some other applications, perhaps weather ensemble predictions, perhaps we're going to have to treat these submitted forecasts as being exchangeable. We haven't perhaps really got a reliable history. Got history of accuracy, I guess we could look at that for some of these, but for some of these teams submitting forecasts, we've got next to no history. So maybe weighted combinations are not going to be so easy to implement. All right, okay, now what are these teams submitting? Well, these teams are submitting forecasts in this form, in the form of probability distributions for each of those 52 series, the US national picture plus each of those 51 states, mortality for each of the next 4 weeks. And they're submitting distributional forecasts. To be more precise, they're submitting forecast in the form of 23 quantiles. Does that look like 23? I hope it's 23. And I'm trying to sort of convey that idea with my dotted lines. So Nick Reich asks them to submit forecasts for 23 specified probabilities, and he wants the quantiles corresponding to those. All right. And what you can see with those 23 quantiles is you build up a picture of the CDF, the distribution function. Should we have a look at the real data? So this was just happened to be the last row in the data set that my co-author and I analyzed. And here we have this is a week ahead forecasting for the final, this is for the final week in January of this year. And this is for, look at the x-axis, US cumulative mortality. So yes, they were getting up to 500,000 at that point. And the forecasters, well, there's quite a lot of agreement in terms of their submitted probability distributions, wouldn't you say? Yeah. But there's one or two outliers, don't you agree? Yeah. These are all probability distributions. I wrote it down. Where have I written it down? It's about 30. It's about 30, 33, 34, 35 cumulative distribution functions have been submitted. That's what we're looking at here. And we seem to have the odd outlier, maybe that distribution function there is a little bit of an outlier. And what about, I've displayed the mean and the median functions there. Yeah, that's very much what Nick Wright does with he produces an ensemble forecast, and that's a summary of all of them. And that's what I want to get into, methods for doing that. Now, one other thing, before I go on to the next slide, I'm interested in this presentation, I'm interested in distributional forecasts, and you've got a bunch of those here. I'm also interested in interval forecasts. And I suppose you could get an interval forecast from each of these distributions. The easiest one for me to talk about is that outlying distribution there, that funny old shape thing there. I suppose if I'm interested in a 95% interval, it would have the 97.5% quantile. Yes, that will probably be this point here. And it would be bounded below by the 2.5% quantile. So that would be that point there. And that's what I'm trying to display on the next slide, all right? From each of these distributions, I could get out upper and lower bounds. Is that okay? I think I was pointing at the blue outlying distribution function. Okay, well, that's the upper bound from that function. And down the bottom left, I suppose that's the lower bound. Yes, it's a bit of an outlier in both senses, upper and lower bound of 95% intervals. But you've got intervals, lower bounds and upper bounds from each of those distributions, and that's what I'm displaying there. And I suppose you could separately look at the upper bounds, and you could calculate the mean and the median in red. And you could do the same for the lower bounds. Look at that agreement between the mean and the median there. Why isn't there agreement between the median and the mean upper bounds? Well, because of the outlier out there, I suppose. Okay. In the next 3 slides, I just want to brush through a few different approaches to combining interval forecasts. And I'm showing you two on this slide here. You can use the mean and the median. So let me show you the mean on the next slide, all right? So this is combining interval forecasts when we're ignoring the historical average of those individual forecasters, all right? We're perhaps assuming that we have poor availability in terms of historical forecasts from some of them. So let's just ignore it. So let's just imagine we've got 5 teams. So that's all I'm showing here, right? I got an interval forecast, and I'm changing. You'll have to forgive me for switching with this sort of visualization. I'm switching so my interval is a vertical line, all right? That's my forecast for mortality, if you like. And that's from team 1. Team 2 submits a different interval. Team 3, I don't know, might be using a different method. Team 4 might be a judgmental forecaster and's produced a 95% interval like that. Team 5, by a bit of a coincidence, that's in blue as well. As that's a bit of an outlying one up there, isn't it? Oh well, what we could do is we could take the mean of those 5 upper bounds and the mean of the 5 lower bounds, and that would be a mean, a simple average approach to combining interval forecasts. Okay, so we mustn't forget that. That's a sound benchmark. I hope that's all right. Anybody got any alternatives to the mean? Well, on the previous slide, I mentioned the median, and if you've got a bit of an outlier, oh, look, he's a bit of an outlier there, a bit of an outlier, maybe we should be thinking of the median. So on the next slide, if my memory serves me correctly, yes, I've got the picture from the previous slide, plus I'm looking at the median. Just take the median and deal with each upper bound and lower bound. Deal with the upper bound separately from the lower bound, of course. Okay, so there's the median of the upper, the median of the lower. Now have a look at this, because there's some quite nice papers that do trimming. They do trimming. Now, if anybody's sort of met trimming in statistics before, trimmed mean, this is a robust approach to estimation, isn't it? Okay, well, the median's robust, but trimmed mean is an alternative. If you look at those 5 upper bounds, maybe you should do symmetrical trimming. Trim off the top one and the bottom one. Is that okay? And take the average of the other 3. That's a trimmed mean. And do the same for the lower bound. Trim off, and take the average of the remaining 3. Okay, so that's quite a nice idea. But actually, what these guys presented with exterior trimmed mean is they said, well, actually, you could do a kind of asymmetric trimming if you took the view that perhaps your interval is going to be, if you do normal sort of taking the mean, it's going to be sort of too unconfident. It's going to be too wide. So do exterior trimming. Trim off the highest of your upper bounds and the lowest of your lower bounds. Exterior trimming. And what about interior trimming? Well, it's thinking of it the other way around. And I suppose the net effect of doing interior trimming is you're going to get a wider interval. All right, so these are the sort of methods that have been proposed in the literature. And I plugged them in for this COVID mortality data set, and they work to differing degrees. But I thought I ought to also perhaps have a go at a weighted method, because we do have history on some of these contributors to this COVID-19 forecast hub. And if you do have some history of producing forecasts, after about 20 weeks, you've got some history. And so maybe you could calculate that interval score to see how accurately they've been producing interval forecasts. That would give you a score, S, for each of your forecasters, I. And then I suppose the simplest approach you could take would be a sort of inverse score method. I'll allocate a weight to each of those forecasting teams inversely proportional to that score. And I've probably normalized it by summing the total inverse scores down the bottom, where capital J, uppercase J, is the number of forecasting teams in the game at that particular week. What is lambda? Oh, lambda's perhaps, if you'll allow me to estimate a parameter, if you feel we've got enough data to estimate a parameter, allow me to estimate just this one. Lambda will be a tuning parameter. I suppose if lambda optimizes, comes out to be optimal value of, say, 0, I suppose that implies equal weighting across each of those contributing forecasting teams, equal weighting across each of those intervals. And if lambda turned out to be a large positive value, if you think about it, I suppose that would mean the greatest weight being put on the most accurate method, the most accurate team, the team that has the smallest historical score. And over on the right, this is just a purely sort of illustrative example. I've just pretended that we've managed to get a score and therefore calculated a weight for each of those 5 forecasting teams in my little sanitized example. And then I suppose you'd allocate those weights, you'd apply the weighting scheme and come up with a weighted average, a weighted combination. All right, so there we are. Those are some interval combining methods. And maybe we could come up with our own approach. Let me battle on, because you could do perhaps similar sorts of things with distributions. So here we are with distribution functions. Can we do the same sort of things with distributions? Well, I'm suggesting you can because I've got mean and median on the slide. Probably could do trimming as well. Probably could do an inverse score approach. And that's what I think I've got in my next few slides. But on the next slide, I'm asking the question, what exactly do we mean by taking the mean of all of these functions? And this rather nice little paper has, I think, a title that's pretty much that. Should we average probabilities or should we average quantiles to extract the wisdom of the crowd? And on my slide here, I'm looking at the situation where we have a very small crowd. We've just got 2 forecasting teams, right? And they produce these gray distribution functions, 2 distribution functions. Now, if you average in a vertical sense, if you think about it, you're averaging probabilities and you'll get that turquoise combined forecast. On the right, what am I doing on the right? Oh, I'm averaging in a horizontal sense. I'm averaging quantiles, actually, aren't I? If you think about it, I'm averaging quantiles. And what you get is quite a different combined forecast. So take your pick. Should we average on the left probabilities? Should we think vertically? Or should we think horizontally on the right and average quantiles? And it's an interesting little topic. And in that paper, they sort of addressed it with a mix of empirical and sort of analytical and concluded that actually one should really is better off averaging quantiles. One of the arguments you can sort of vaguely see on this slide is it's giving you what they call a sharper distributional forecast. Okay, the one over here, it's typically underconfident. It's typically too spread out if you average probabilities. So the recommendation is to think horizontally and average quantiles. Okay, so a bit of an exposure. These slides are you're very welcome to have these slides, and I've got a list of the references at the end. So this is just a quick brush overview of some different combining methods. So in the spirit of averaging quantiles, thinking horizontally, am I okay at top right on this slide? Is that okay? Top right? I'm thinking of 4 forecasting teams, each of which has submitted a distribution function. Is that all right? A distribution function. Oh, we've got one that's a bit different from the others, a bit separated off, perhaps a bit of an outlier. You could take an average of those 4 grey distribution functions, think horizontally, and I suppose that would be the combined function there. What's going on down the bottom? Oh yes, trimming. Another rather nice paper produced by, well, some of the same authors actually as the previous paper I mentioned. And what they're doing is trimming. And so let's trim. Let's think horizontally and let's trim. And in dotted lines, I'm highlighting the distribution function that I've just trimmed. Let's trim from the lower and trim from the upper and then take the average. So that's a kind of robust approach, isn't it? A robust approach. And it gives you quite a different distribution for this sanitized little example of 4 distribution functions, 4 distribution forecasts. Okay. And on this slide, I'm just sort of saying, well, if you kind of bought into the idea of inverse score, inverse interval score before, when we were doing a weighted combination of interval forecasts, then I suppose you could sort of do the same for distributions. The CRPS I did mention was a score for distributions. I mentioned that early on, didn't I? Okay, the lower the better. Perhaps I forgot to mention that, but the lower the score, the better. And you could use that score in this inverse fashion to derive a weight in order to do a weighted combination of your four, in this case, your four distributional forecasts. Where did these numbers come from? Just an illustrative example. Yep.
James is Nachi. So just want to give you like a heads up, or maybe we go for another 5 to 7 minutes and then allow a few more questions. Yeah.
Yep. I don't like questions. I told you, Nachi, I don't like questions. I prefer to just use all the time with me blabbering away. So yeah.
We'll try and squeeze in 1 or 2 at least.
Well, it's okay. I've very much got my eye on the time, so I won't overdo it. But okay, so there's a sort of inverse score approach. That's sort of analogous to the inverse score for interval forecasts. All right, let me just put up briefly some findings. Now, of course, findings are important. This is an important application, COVID-19 mortality. But I have to admit, I'm sort of a guy who's rather interested in methods. So let me be brief here and get on to talk about 1 or 2 other methods we could try on this sort of data. In summary, from our empirical work, we found that median combining, whether you're talking about intervals or distributions, you want a method for extracting the wisdom of the crowd, median works better than the mean early on. But thereafter, use the mean, seem to be more accurate. Once a history of accuracy starts to become available, actually what is in our empirical work clearly better is to use an inverse score method for combining intervals and for combining distributions. What about the individual teams? Yeah, a couple of those were very competitive for incident mortality. Not for cumulative mortality. I couldn't really evaluate it because none of them were available for my full evaluation set of weeks. And there was fairly similar performance, whether you're talking about 1 week ahead, 2 weeks ahead, 3 or 4 weeks ahead. Right, okay, so that's findings, and we produced a paper on this. You're very welcome to have it. Anybody has any queries, if I don't leave time for questions at the end, or anybody wants the paper, very, very happy to send it to you. So just zap me an email. Okay, but now for something which is a little bit more innovative, perhaps, on the methods. I'll give myself 5 minutes, Nachi, just to talk about this, because I think it's a slightly different way of doing what I've been talking about so far. You see, what I've been talking about so far, certainly when it came to median combining of these distributions, and I've got 3 in my picture here, 3 distribution functions. If we're thinking about median, if we're thinking about trimming, it was very much piecewise. That's what the literature has said. Look at it in a horizontal sense. Look at it in a horizontal sense and find the median. And I think you'd sort of agree that the median was actually this part of this particular distribution function. Oh, and then it switched to be a different part of a different distribution function. And then it was a different part of the other distribution function for the lower quantiles. So actually, we're doing it very piecewise. And I just wonder whether that's wise. What if you perhaps had, and you have seen these pictures before, what if you had an outlier function? Maybe you shouldn't be doing it piecewise. Maybe as soon as you see that you've got a function that seems a little bit of an outlier in terms of the upper part, you should actually use that information to judge whether it's an outlier, and you should strip it in its entirety potentially from the combination. And perhaps this is also another outlier there in this sort of mustardy yellow. Down the bottom, the point I'm trying to make is don't look, and I did say it earlier, don't look separately at the upper bound from the lower bound. Earlier, I was showing you methods that look separately at each bound. What I'm suggesting now is that as soon as you see you've got an outlier for the upper bound, maybe you should eliminate the lower bound as well. It gives you information about that particular forecaster. Sorry to sound so harsh, but as soon as I'd seen that outrageous upper bound, I would have eliminated that forecaster from the game. All right, and we've got that mustardy yellow. Take note of that one as well. That's a bit of an outlier, isn't it? Much less of an outlier in its lower bound. Right, okay, get ready for sort of perhaps the most confusing jump in this presentation. We've got here some sort of visualization of a collection of about 33 different interval forecasts. 33 upper bounds, 33 lower bounds. Now take note of that blue there, right? 510, agreed? 510 was the upper bound. And the lower bound was about 420, agreed? Let's look at them as a pair. That blue, the upper bound, what did I just say? 510 roughly. And the lower bound? Oh, about 420. So I'm taking each of those pairs of bounds, those interval forecasts from the previous slide, and I'm putting them on an XY plot. Each of these points represents an interval. Now, if I look at the cloud of points, and I've got one out there, I would say that's an outlier. That's not terribly informative versus what we saw on the previous slide. But I think this is a different way of looking at a bunch of interval forecasts, a crowd of interval forecasts. How do we decide which is the median? And for this, I turn to a very mature literature on statistical depth. Statistical depth enables us to do a sort of a ranking that exists in a trivial way for a univariate, for a variable, for a univariate set of values. We can extend to the bivariate with concepts of depth. And there are different measures of depth. And I've got one at the bottom of the slide, and I've used measure of depth, and I've found that actually that particular data point, that particular forecaster, that particular interval with a big pink cross on is the deepest, according to using Tukey's measure of half-space depth. Oh, and this point here, this brown, can you see that little point there? I don't like it. It's on the perimeter of the cloud of points. And I'll tell you why I don't like it. It's not in the heart of the data. And I'll tell you what's slightly interesting about that brown point there. If you think about it, it's probably about the closest to an x equals y line. And an x equal y line, I suppose, would correspond to an interval where the upper and the lower bound are equal. That little brown point there is the narrowest of my interval forecasts. Yes, that is in a sense an outlier. It's certainly not in the heart of the cloud of points. The use of statistical depth for a bunch of interval forecasts, and we can do the same. We can do the same for the distribution functions, and we'd be using their functional depth. And there are lots of ways of deciding what is the deepest of your functions in amongst a set of functions like this. The spirit of this is don't look piecewise when you're carrying out your trimming or you're finding the median. Instead, search for not median piecewise, but search for the median forecaster. That's the spirit of what's going on here, the deepest forecaster. All right, Nachi's going to come after me with a big stick if I don't finish soon. But that's my current sort of hobby at the moment, is playing with statistical depth. So that's another paper that I'm sort of, I like to think, well on the way to sort of finishing. And I'd love to send that to anybody who might be interested and hear what they have to say. So let me just so I complete my brief, just say that there is this other wonderful data set, the US Survey of Professional Forecasters, that's been used by many people experimenting with methods in this broad area. Wisdom of the crowd for interval and distributional forecasting. And yes, it looks at just, well, it focuses on two particular economic variables. And it's a similar sort of game, really. Look at the numbers over here over time. Similar sort of number of forecasters in this particular survey. similar sort of numbers for each of these two different variables, and similar sort of pictures evolve. I'll put up just this one because this is slightly interesting, because at the start of Q1, the start of last year, these were the distributional forecasts for US growth. Okay, what was the economy going to do? It seems that there was fair agreement on the uncertainty and fair agreement on, I suppose, their best guess. They're all sort of saying it's going to be about 1.5%. COVID hadn't quite taken off. 1 quarter later, their forecast was somewhat different for 2020 growth, and they were predicting very different, as low as sort of, I suppose, this sort of percentage growth, which is quite a drop in the economy. It turned out that it was, I think, a drop of 3.5% actually last year, so not quite as bad as perhaps the general picture. So yeah, the distribution shifted to the left, didn't it, a quarter later into the year, but also quite a lot of, I suppose, disagreement amongst those 30 or so distributions submitted. All right, let me shut up. 4 minutes left for questions. Not many at all. And I haven't even summarized, so I shall keep talking to use up all the time. I won't summarize. I'll just say that it was all about interval and distributional forecasting, so Nachi doesn't get completely cross.
No. Thanks a lot, James, for this fascinating talk. So I think we have just enough time to maybe squeeze in the couple of questions that have come in. So the first one was by Richard Lay, referring to an earlier part of your talk. His comment/question was, I suspect that asking the audience works best for easier questions. What do you think?
Yeah. I mean, I don't claim to be any great guru on wisdom of the crowd. I'm very much sort of a researcher in a specific part, but the same occurred to me when I was reading about, Who Wants to Be a Millionaire? I mean, they'll probably go to their trusty friend when they've got a tricky question, and they'll only ask these idiot-looking audience when they've got an easy one. So yes, probably that's a very sort of silly example.
Okay, so hopefully that'll answer Richard's question. Liz Bentley asks, could you apply this to weather or climate forecasts where there are multiple parameters that need to be forecast over numerous time steps?
I don't know. I don't know. I'd have to understand the question in a little bit more specifics. I mean, statistical depth undoubtedly could be used, I think, in lots of places where it hasn't been used so far. My specific interest here is using it to, I suppose, extract the wisdom of a crowd of probabilistic forecasts. Now, you talk about climate, you talk about, say, weather forecasts. I certainly think my own playing with weather data, I had a lot of fun playing with weather ensemble predictions. And the typical sort of way we visualize those is those spaghetti plots, looking at sort of projections of multiple different projections out into the future from these 51 different ensemble members. Each of those is an ensemble member. Well, let's calculate the mean for each of those periods out into the future. Oh, let's not do the mean, let's do the median. Oh yes, let's do the median separately for each period out into the future. Well, you could actually not do either of those and instead look for the deepest of those different realizations out into the future. You could use statistical depth. I suppose that would be functional depth to find the deepest of the 51 ensemble projections out into the future. So that's me going off on a bit of a tangent, but I played with weather data a bit in the past. I'm certainly not a weather forecaster or meteorologist, but I'm sure that doesn't answer the question. But I'd love to get hold. I have played with a little bit. I did get hold of a data set on climate projections. It was from about 70 or 80 climatologists who are giving interval forecasts for some aspect of climate 100 years in the future, and how best to combine those 80 or so interval forecasts. Well, I've got my method. Somebody might have theirs. The trouble is we won't know for 100 years who's perhaps got the best method.
Okay, just want to check with Luz if there's another question. Do we have time for another question before we wrap up, Luz?
Yeah, absolutely.
Okay, great. So Dean has asked you, have you looked at Philip Tetlock's work on political forecasting? Very interesting.
Well, Philip Tetlock's, and his work on super forecasting. So for sure, I mean, I've got the book and I've read most of it. So yeah, I mean, that's another way of looking at a crowd, isn't it? So there's me sort of, I suppose a super forecaster can only be established if you look at accuracy, and the spirit of the sort of data I've been playing with has been this troublesome problem that we don't really have accuracy. Or we don't have a reliable accuracy, comparable accuracy for many members in the team. So therefore, actually, the spotting of a super forecaster, bringing in Philip Tetlock's work is not so easy, but for sure, that's a load of fun. And actually, that community is really close to the community that I link to with my sort of research. And let me just say 3 numbers. 538 website. Another guy who's written a number of interesting books is Nate Silva. He's the guy behind the 538 US website, which is a kind of, what do they call it? A data journalism sort of website. And Nick Reich's COVID-19 forecast hub set of forecasts are being put up week by week, or they certainly were, on the 538 website. So yes, it's a small world in all of this. So yes, Dean, I don't know as much as I should about Philip Tetlock's work, but I know some of it.
Okay, great. Thanks. Robert Bowden, you can unmute yourself and ask your question. And this will be the last question, I guess, in light of time.
Let's hope it's an easy one.
Yeah,
Robert?
Sure. Robert, can you unmute yourself? Or let me try to unmute you.
We cannot unmute you. You have to unmute yourself, please.
No, it wasn't a question. It was just a comment, really, just to thank James for an interesting presentation.
Well, thank you, and thank the Reading group of the RSS again for inviting me along. Yes, don't know what I quite did to deserve this great privilege and honor. And thanks everybody for turning up to listen to me. Thanks for your patience if you managed to survive to the end. It's not everybody's cup of tea, but it's stuff that sort of interests me. And if anybody'd like to get in touch, I mean, I think you'll find me. James Taylor is a dead common name, but you can narrow it down to sort of Oxford University, and you might find my email address. And for goodness sake, get in touch if you think you've got any sort of data that I might like to play with, or might be able to contribute towards.
Yeah, thank you, James.
Thanks a lot, James.
Thank you. Thank you.
And thank you to all the guests for joining in and staying on. Thanks a lot.